Hello, my name's Kevin Starr, and in this episode of Single Loop Control Methods, we're going to be talking about dealing with dead time. You may be thinking you've done that really well through all the previous videos, but we're going to talk about dead time as it applies to a process. And that's what we're going to get into here is when we talk about process control, we started our whole discussion on what is it, and when you're dealing with dead time or delays in a process, there's a point at which traditional control tuning, you have to go to a more advanced control algorithm. And that's what we're going to cover, or at least introduce to you in today's discussion. So what is internal model control, or Smith predictors, or modified Smith predictors? How do I deal with dead time? What's a 3-parameter model versus a 2-parameter model? Model mismatch is going to become a much bigger discussion in today's presentation. In our previous talks, if the dead time got big, we would just go with a larger tau ratio, a 4 or 3, something very conservative. But at some point, the response is so slow, you actually have to update the process model and then change your tuning or your control algorithm to match that. That's what we're talking about in this particular episode. There are several links in the chain of process optimization, starting with especially with dead time. I still like to start with a PID algorithm and try to tune it as aggressively as I can, but when it gets to where it's just not fast enough, there's only so much you can do with tuning, and then you have to go into dead time compensators or predictors. And that's what we're going to talk about. Many of today's control systems have a function for dead time compensation, and that's what we'll show you, and you'll be able to align that as we go through. Basically, if you go and you change the actuator and the process takes a while before it starts to respond, that process where nothing's occurring is what's called dead time. You may hear it referred to as delay, delay or dead time. It's from the time you make the change until the process starts to move as a result of that change. In our previous discussions, that has been very, very small as compared to the time constant of the process. So basically, we absorb the dead time in the time constant. There are processes that get quite slow in terms of the dead time, and you can't do that and still get nice regulation. One example is a paper machine, or think of a walkway at an airport. You hop on it and you stand there and then you get off. It's the same kind of thing. Is from the time you have an input to this particular process, it takes a while if you're measuring it at the other side. So that's usually one of the considerations. If you have the chance when you're building a process, is make sure that the actuator and sensing device are as close together as you can without affecting the process dynamics. Sometimes you physically have to move the transmitter and the actuator. They're physically separated, and that when I move the actuator, the process has to move, and then you see it. That's dead time. So how do you deal with that? That's what we're talking about. Traditionally, up to now, we've been talking about a single loop control situation where I have a controller, I have the output to the actuator, and then I read it back. So in this case, there's only so much you can do with a PI algorithm, and that's what we're going to get into. Up until right now, we've talked about 2-parameter models. Those 2 parameters being how much did it move and how long did it take to get there. And we referenced the start of the change in the output. In this case, that parameter no longer holds true, because you can see this section in the middle is what we call model mismatch. And I still recommend starting here, and this is a throwback from our discussion that we just had, where you calculate the time constant, and you can see the dead time is rolled into the time constant. So that's this little tick or this prime. It's sort of a calculated time constant. Sometimes you'll see a little hat or a prime. It's not the real time constant. It's made up. So 4 of those time constants is when it settles. But it's really the dead time plus 4 of these. But it's still the same equation for the proportional and the integral, and there's no derivative. Now, as we get more elaborate, we can talk about how to handle that with other constraints. So here's what that looks like. I've shaded the area. That's called model mismatch. And remember, we were talking about the tau ratio kind of allows you to set the target size. It's like if you're shooting arrows, you may group really well, but they are all together and they're not at the center. Our algorithm that we showed, it was assuming that you had a first order response with very little model mismatch. And as your model mismatch grows, you have to make your target bigger. And as your target gets bigger, your set point response or your regulation capability goes down. So the question is how can I get, if I know my process responds the same way every time, but it's not a first order process, how do I recalibrate my model so that the center is now where I'm grouped? And that's where a 3-parameter model comes in. So when you look at this, this is what happens, and you'll see this when you have a standard PI or even a PID algorithm without the dead time compensation. Look at this ramp. So what happens is I change the set point. So I changed the set point, the control said I need to make a change, that's is proportional to the error, and then it's expecting the measured value to start to move. And what happened is the measured value isn't moving because of the dead time. Well, remember what integral is? Integral is a watchdog. It's like, hey, it's proportional to the area under the curve. So what happens is you get this ramp during the dead time. Well, the PI algorithm doesn't know that the change is coming. So what happens is if you kind of draw a line from where you ended up, this is all too much valve change. And what happens is you get an overshoot. So with this traditional PI algorithm, with dead time, you will always get an overshoot because you integrate during, so the amount of time you integrate is how much extra movement you get in your actuator. The extra movement results in an overshoot. And we'll show you in a little while that that can actually become it's a destabilizing parameter in your structure, which means you can cause a loop to go unstable when you ignore dead time. That's what we don't want to do. This would be the ideal. The ideal would be if we could sort of pretend that the dead time happened after the primary dynamics. So you can see here, if we could split the process apart. Remember, there's now 3 parameters. There's dead time, time constant, and process gain. And traditionally, when we're doing things in our head, we think in terms of dead time, time constant, gain. But wouldn't it be nice if we could somehow flip that around, that the time constant and process happen and then the dead time happen later? And if we could measure the process before the dead time happened, we could then control it with the PI algorithm just fine. And we would get this kind of response, which is really what we want. We want to make the set point change, we want the output to do what we want, and then realize that it's going to take a little while to get there. That's the ideal, and it's taken 30 years before technology allowed us to do that. And that's what I want to cover here. And that's the question. How do we do that? How do we measure the process without dead time? Well, you can't physically measure the process, but we can simulate it. And if we simulate it, then we can pull from the undelayed process. And that's what we're going to talk about. There's 3 primary standards, if you will. Smith predictor was the first, and you can Google Smith predictor, and that's a very well-known S-domain Laplace classic control algorithm that deals with that really well, and I'll cover that. There's a version of the Smith predictor called the modified Smith, which is a logical change, and I'll share that with you. And then there's the internal model control, or sometimes people refer to it as IMC, and it uses what's called lead lag technology, where the Smith and modified Smith use our old friend PID. The IMC uses what's called a lead lag technology, and we'll cover that. So the idea here is to first we have to calculate the process. We have to figure out a model and then break it up into its parts. The idea of process modeling needs to be looked at a little bit more in depth. We have to break it up into its pieces. We have to be able to think in terms of dead time, time constant, process gain, and actually think of them as processes. So what we're going to do here is actually step us through a simulation and compare it to the actual process. And I think that will make sense. So we have 3 parameters, 3 parameters that we're looking at: gain, dead time, time constant. So what do those look like? To recall or refresh, the pure gain part of this is the change in measured value over the change in the output. It's what we covered before. It's how much did it move for a given change. That's not any different. Time constant, by itself, it's from the time the process started to change until it finished divided by 4. We already talked about that. 63% of the process is where it's going to go at one time constant. And that's a first order or a one pole process. Dead time is how long it takes for the process to start to change. So those are the definitions. Process gain is the same as before. Time constant is the same as before, except we're starting it from when the process changed, not the actuator. That's a big difference. And then dead time is from when the actuator changed until the process starts to move. Those are the three pieces that we have to kind of understand. Now this is an example where I went and did a bump test up at the top, and you can see it trickles along, and I have at time 0, I'm just showing at time 0, that's where the bump occurred, and then at a time equals the dead time, it's when the process started to go. 4 of these time constants it reaches, and it goes a process gain times the input. That's what we're looking at. Now how can we break that down into its pieces? So we start off with the process model. Or the simulation. So let's start with the gain. If I have a step input into a process gain, what would you expect the output to be? Just think about it, maybe draw it. You know, maybe get a piece of paper and say, okay, if I step input into this, what should it look like? Well, it should look like the same thing, because all we're doing is it's a transfer function. So we're transferring that step change and we're multiplying it by a gain. So if the gain is bigger than 1, it'll be bigger, or less than 1, equal to 1. That's the transition. Now let's say we run that into a time constant or a one-pole process. What would you expect to happen? Remember what a one-pole process is. It's got this lag. It's a lag agent. So if I inject energy in a step, what would you expect the output to be? So draw it down and see if you got that. It should look like a first-order process. So you can see so far we took a step input, you went out, changed the actuator. Then it went through a gain. We scaled the change, and it went through a time constant, and we decided how long it took to get there. Now we run that into a delay. Now what do you expect to come out? The only thing a delay does is it's sort of thinking like a Ferris wheel and all the buckets. Sometimes they call that a bucket brigade. So we put something in one, and then it comes out. So the amount of rotation is the dead time. That's sort of how my head works. But that's how these delays work, is they kind of shift buffer registers and out it comes. So what we should get is exactly what we put into it, only delayed by the amount of shifts or the amount of dead time. So what we have here is we have recreated the process. So this is our simulated process based on an input. So if I have the same input to our actual process going into our simulated process, what should the difference be between these two? Noise or load changes. Anything that is not related to the actuator. Now we're getting close, and we're going to come back to that. That's really what we're doing here, is we take the input. This is where, if you look at a Smith predictor, it's wired like this, and these are actual now inputs into the software model. Some people call them tuning parameters. I call them setup parameters. In the traditional PI algorithm, you use the gains to calculate, you use the process model to calculate your controller gains. In a dead time compensator, you actually have to enter those model parameters into the software, because we are simulating the actual process. That's what's happening under the hood. And so what you see here is we have an input going to a gain, time constant, delay. So what we should get, in the absence of a disturbance or noise, the measured value or process value and the estimate should be exactly the same, which is what I'm showing here. That's the trick, is to get those together. And when those are right on top of each other, your model mismatch is 0, and then we can be much more aggressive on our tuning. One thing I just point out here, a lot of people, when we're doing this doesn't actually subtract dead time from the process. It still takes that long to show up at the sensor. But internally, the control is expecting the process very, very fast. It doesn't actually take out dead time. This isn't a dead time. You actually have to move instruments to replace dead time. If you can do it, that helps immensely. But this is just a software, we're faking out the controller. And that's what we're going to show here. Is now take a look at this, is now we slap a controller on the front end of this. So the output of the controller not only goes to our physical process, it actually goes to our simulation of the model. And what we've got is the gain and the time constant, and then our feedback is right before delay. So this model, look at this path right here. This is a simple first order model. gain and time constant. So what do you think the controller should be for a simple gain and time constant? If you go back to our earlier discussions, it's a PI algorithm. It's simple. So it's a Smith predictor is a PI algorithm. Now, I may have gotten just a scooch ahead there, but what's the problem with this? Why not just put this in? Because in the real world, there's two things that affect our process. One is the actuator, the other is the load. When the load occurs, you can get an offset, and because this load is not in the feedback path, your controller never makes a change. So actually, this was the original embodiment of the Smith predictor. Is it worked great on set point change, but then when they had a load change, he resulted in an offset. People are like, well, now what do we do? Well, take a look at this. What would you do? How do I get this load into this feedback path? So you take a look at that. What's the secret? How do I get this information into here? Well, the answer is in the absence of load, this measured value and this estimate should be the same. So what if I just subtract these two? Because this is really equal to the actuator through the process and the load. So if I subtract our actuator, then what's left is the load, and that's what we do. That's the picture. So if you look at any of your textbooks, if you do this Google search on Smith predictor, you'll see something that looks like this, where your controller and your actuator are tied to, that's your physical analog output going to your process. Your process does its thing. We measure the process, that's the sensing device, but we also sum it with the estimate of the process. So what we have here is the load. It's this minus this, that's the only difference. And we add that into the process. So literally, we can now change the set point. It works great. And if we have a disturbance, it'll regulate it. That's the secret to the Smith predictor. And it works if you plug in the process model, which you got from doing a bump test. Then, that's what I was talking about earlier, is if you look at the feedback path from the output, this feedback path is a pure first order model. So this is a simple PI algorithm. It's what we talked about before, where you can use tau ratio, you can use 1 over kp tau ratio, and your integral time is equal to your open loop time constant. And then you pick the speed of the response, knowing that the dead time's still there, but now you don't get that overshoot. And that's the secret. So when you have long processes and you can't allow overshoot, you can't use a PI algorithm. You have to use a Smith predictor, and that's what's the beauty of this. So you get that. So I change the set point, control does its thing, control comes up, it's perfect. It looks like the ideal that we started with. And that's the beauty of the Smith predictor. Now, people started to kind of adjust the Smith predictor a little bit and said, well, how could we reduce the complexity of the controller? So what they did is on a Smith predictor, they pulled from this point in. From a modified Smith predictor, they said, well, let's just pull it out of the gain calculation. So if we look at this, what's our control loop? Our closed loop. It's a pure gain process. Remember, if you remember when we talked about identification, I said there's no such thing as a pure gain process. In the real world, this path, that's very difficult to do unless you sample really slow. But in software, you can just feed back anything. So when you feed this back, what do you need? I have one parameter. What do I need? I need an integral only control. This is actually, when I first started years ago in the pulp and paper, our 1180 micro used this technology to simplify the difficulty in tuning. You had one number. You entered the same model, you entered one number, and you were done. So it was very robust. One of the issues with that early technology with the integral only is you don't get that kick in the, if I go back a couple slides here, when I change the set point on a Smith predictor, I get this kick. It's as a ratio, it's a function of your tau ratio. So your closed loop response is faster. On a modified Smith, you don't get that kick because it's an integral only control. So what happens is it's a little bit slower. Notice you kind of get this S curve in the measurement. It's a very stable control, and on those early applications, that's what we wanted. So this worked great, and actually that control has run for over 30 years. So it's not a bad idea, but it's a little bit slow. Now, when we went to sort of more modern distributed control systems and more function blocks that could be brought into software, we were able to do a lead lag compensator. Lead lag compensators are very difficult to do in the analog world. but they are very easy to do in the world of software. So that open up another area, and that particular area is called internal model control. Now, all of these model predictors require us to calculate the process model. And what I want to show you here is just to sort of introduce the format of a dead time model in what's called the S domain. And that's if you have your process gain, you have your dead time, and you have your time constant. So you have your input goes through this model and you get this response. This is what it looks like, and I'm showing that because in some control systems it will plot it like this. Just, you don't need to understand the S domain or the Laplace domain, but if you see this representation, if you see whatever they have up here, that's your dead time, whatever you have here is your process gain, and whatever you have down here is your time constant. That's the only reason I'm showing you that, because some of the manufacturers show their internal model control or their lead lag compensator in this format and say this is what the model is. There's just still 3 parameters: gain, dead time, time constant. Now, in this embodiment, what we were wanting to do is, instead of trying to pull the process in from, this is modified, this is Smith, they're like, well, what if we just take the input, they take these and run that back? Well, think about that for a second. Why won't PI or I only work? Well, what is this? If there's no load, what's the difference between these two if this model and this model match? They should be 0. So basically, your error path is 0, your set point might be 30 or 50, whatever, and your feedback 0. So in a traditional controller, that difference is the error, and that's why we couldn't use PI or PID with this embodiment. But a lead lag compensator, it doesn't matter, and that's what I want to show you. So here we said, let's just take this and run it into our controller. But we can't use a PI, we can't, because the feedback path is literally 0. So how's this going to work? Well, that's what I'll show you. In general, we have this question mark represents the controller that we need and the process, which we've been talking about. So that's the question. What kind of controller do I, if I can't use a PI or a PID or an I, what do I use? Well, it's called a lead lag compensator. A lead lag compensator is one that shapes the input. And it's easy to see it if the input is a step change. So here you can see a step change. In a lead mode, where the lead is more dominant than the lag, you get this kick. Okay? A lot of people call that like derivative action. That's not really it at all. It would be better to relay it to tau ratio. This would look like a tau ratio of less than 1. I could actually calculate. It's like a 0.5. It moved twice to where it went. So that's a tau ratio of 0.5. That's a lead action. We're trying to make the process respond faster than it would by itself. The middle here is a direct transfer. We went from the step, so it's be like a process gain of 1. It just transfers it through. Okay, do you see that? And then a lag is where the lag element is more dominant than the lead element, and so what happens is that step change gets slid out. This looks more like a tau ratio. Actually, we could calculate that. What is that? If it moves half of where it's going, what's the tau ratio? 2. So you take your total change divided by your initial change, that's your tau ratio. That's maybe, that's another trick. So I can look at that. So we can have a lead lag compensator. We can tune it as if it was a tau ratio of less than 1 or greater than 1. So we can make it respond fast or slow or pass through. Aha, that's the beauty of a lead lag compensator. If you come from an analog world where you're doing pneumatic stuff, you can't do that. Everything's lag. But in electronics, we can do this. And in software, we can do this. And so now we've got something. Now, mathematically, it gets a little bit complex, but just sort of bear with me here. If we talk about a lead lag compensator, this is traditionally how they are displayed. There's a lead element and a lag element and a gain. And so remember our process, we have a gain, a lag, and a delay. Okay? So if we align the lead element of the controller with the lag element of the process, when these are multiplied together, they cancel. And if we take the lag element of the controller with if we take the gain element of the controller and the gain element of the process, we can cancel those. So what's left is a process delay and the lag of the controller, which is a first order response with dead time. So we have something. If we use a lead lag compensator, take the difference between the measurement and the estimate and feed that in, every time we change the set point, we can make it go fast or slow, just like the tau ratio. That's what with the kind of the breakthrough with the lead lag compensator, is it reduced the complexity of the control and where we, and where we tap into our simulation. So this is what we're saying is an internal model control. If I change the set point and I have the lead action is more dominant than the lag action, I can get this valve to respond this way, so it responds really fast. Remember, we're not taking out the dead time. That's still in the process. A tau ratio of 1, you notice I step, they're the same. And here a tau ratio of greater than 1, so it responds exactly as if I was using a PI algorithm with our tau ratio tuning. But we enter in the delay, the lag, and the gain exactly equal to the process model that we calculated. And that's the beauty, is a lot of, and that's where it's also tricky, is some of the internal model controllers, you have to enter all these parameters. Some of the model controllers, you enter the model and it calculates the tuning for you and you just enter the ratio. So you'll have to look at how your particular implementation of this is, but that's not so difficult once you map this to how your particular situation is working. So this is what it looks like. Your valve goes into your process. So now if we have a load, the load is fed back, so it works the same way. For a set point or a load, it works the same way. This is what it looks like. You may see this as a block diagram where it's a lot simpler embodiment. They're called function blocks or control blocks. It's one control block. And a lot of times you have so it's a much easier implementation in software to do an IMC controller. So you can see your lead lag. And typically what they do is the successful implementation of a dead time compensator is entirely dependent on the accuracy of the model. And I'll show you that here in just a minute. If the model's wrong and you subtract the measurement from the estimate, it doesn't know that that wasn't a load change. So when there's a load change, it makes a correction. So whenever you make a correction for an error, that does show up in the process, and you can destabilize this if you're. So that's why bump tests if you're using dead time compensators, you should put bump tests as a regular preventive maintenance to make sure the model doesn't change. Because if the model changed, you just injected error into your final what you're measuring and trying to sell. So that's what I'm saying is it's very important. Model mismatch will show up in your process. You should do regular bump tests to make sure that your model's not shifting over time, or it may be seasonal, or it may be dependent upon production lines. I've run into all of those, so you have to be careful. And so this is the kind of the rule of thumb. Again, for a purist, you'll not like it, but the rule of thumb is if the dead time is greater than 3 times the desired closed loop time constant, then conventional PI techniques just don't work. So that means, if our dead time is really big and our closed loop response and that ratio of 3 is in there, you just can't do it with a PID, because your integration over the dead time will be so much, you'll result in ringing. And you just have to go to a dead time compensator. So that's what we'll take a look at here, is the example when there's no mismatch. So here we have no mismatch. So you can see, well, very limited, it may be noise. So what you have is this limited mismatch. So the difference between the measurement and the estimate is flat. So that's great. But what happens when we have mismatch? See, before we could just go with a low tau ratio and you just were a little sluggish. Here, if we have the wrong time constant or the wrong dead time, this difference actually shows up in the feedback path. The controller doesn't know the difference between a load change, set point change, or a model mismatch. So it's going to make a change. So whenever you fix something that's not a problem, it is a problem. And that's what I want to kind of illustrate, a worst case scenario. All dead time compensators, not just ABBs, it's all of them. This is what happens is I'm showing how we can amplify a certain range of disturbances. Now there are ways to mitigate that risk, and I'll show that. So we're going to jump just a little more advanced here, is take a look at this oscillation. Let's say, here's my bump test. I did a bump test, I have this delay, so you can see that's a physical bump test. Now what I've done is I've set up a disturbance that has a period, it's twice that dead time. So here we've got this disturbance just rolling along, and I've aligned all this for the worst case scenario. But I've got this disturbance it's just always there. Okay, I turn control off over here, the process is impacted directly by the disturbance. So this vertical line here represents when I turn control on. So here the process is being affected by the disturbance 100%. With a disturbance that is exactly twice the dead time. Okay, that's the setup. Now I turn control on, so now I have a set point. Okay, this is my reference where I want to be. Now I happen to turn it on exactly at the point where the air starts to grow. What's the controller going to do? My air is moving. It's going to move the actuator. When does the actuator change show up in the process? Exactly in the wrong spot. So this change will not happen until the dead time, exactly at the time that the disturbance. So what happens is I amplify. This is just as simple as I can, I mean it's not that simple, but it shows the amplification of a oscillation with a period exactly twice the dead time. You get it, and so in internal model controllers, you have to be aware of that amplification factor. One nice thing about dead time compensators is you can limit it to, I think it's 2 or 3 times the amplitude based on aggressiveness of tuning, where with a PID algorithm you could jump up to 50 or 100 times. So you can stabilize greatly these disturbances with a dead time compensator. Now that's what it looks like, and so what we have done, and some manufacturers will provide this feedback filter. What this feedback filter does is it attempts to attenuate disturbances in the frequency band that we actually make worse. So there's a little bit of thinking to set this filter up, but you don't have to use it. If you don't have a lot of disturbances or you can measure them, it's not really a big deal. But if you start to see your frequencies or you have a lot of noise, you would like to put a little bit of a filter in here to kind of attenuate the energy that we can't do anything about anyways. Now, this is what's called a Bode plot, and we're not going to spend a lot of time in Bode plots. We talked about that when we talked about cyclic energy and what happens. But in that discussion, we had a real simple first order response where we attenuate frequencies over here and we pass frequencies over here. Whenever dead time is entered into the process, you produce an amplification pattern. So you can see here that in this from the cutoff over we can attenuate, but then we amplify. But then it's, we can exactly, if you can imagine, my example I showed is I had the perfect storm where the oscillation was such that it amplified. If I tweaked it a little bit, our correction would happen exactly at the right time and we would cancel it. So those are the benefits. So the trick is to mitigate the risk of these amplifications and try to maximize the attenuation. But this is what I just wanted to illustrate, that whenever you kick up the complexity of your controller, if you go from PI to PID, you have to have a higher order model. When you have dead time that is significant, you have to go to a dead time compensator. It is more complex. When you have more complex algorithms, you have to have more frequent checks on the process, because if the process changes, you can push a loop into oscillation. When we started all this thing, we said, what is dealing with dead time? We've introduced a 3-parameter, I did that again. We introduced a 3-parameter model where you have your gain, how much did it move, your time constant from the time the process moved till it ends, and then your dead time from the actuator to the process. We talked about a Smith predictor where we could actually use a PI algorithm. We talked about a modified Smith predictor where we use an I algorithm, and we talked about an internal model control algorithm where we used a lead lag compensator. That covers the range of classical control applications that you're going to run into. Many of our manufacturers and vendors have one of those options to pick from. So take a look at your technical documentation, look at this presentation and play it back a couple times. But the tuning algorithms match exactly with what we covered in the earlier session on tuning. So with that, we finish our presentation on dealing with dead time.